Yeah, this is the example that we finished with yesterday. And I was reminding you to always check your answer and make sure that your answer passes the reasonable test. Like, for instance, this is not related to the gas laws, but for an example. Now, I always want you to think about the answers that you get. And if you are asked about a molar mass, if the question is like, here's some information about an acid-base titration, determine the molar mass of the gas. If you come up with a molar mass of 0.089 grams per mole, don't just say, oh, my calculator gave me 0.089, so that must be it. It's going to be wrong for sure. So think about it. Think about what you get. Why is 0.089 not a good molar mass? Yeah, the lightest thing that we know of has a molar mass of 1. That's hydrogen. Nothing has a molar mass less than hydrogen. So what might you have done? Well, you maybe forgot to change into liters from milliliters. You may have divided upside down someplace. So, think about stuff like that when you get an physically impossible answer. So we got this. This is a really high pressure. I mean, when you get this answer on your calculator, I'm hoping you look at it and think, man, that's a big pressure. That's a lot of torque. But then when you look back at what happened in the problem, you can justify it. Oh, I see. Well, the volume got compressed a lot. The temperature went up by a lot. So we should have, a significant change in the pressure. Okay, so we'll talk about that as well when we do this next thing. The last gas law that we have, Graham's law, another German guy. Lots of laws named after German people. The Germans, back in the 1800s, early 1900s, that was really the hub of chemistry and physics. They were doing so much over there. A lot of big discoveries made by people over in Europe. So yeah, Graham was Otto Graham. And this Graham's law is a comparison between two different gases. You will never use Graham's law for a single gas. So that's something that I want you to keep in mind. You'll only compare two different gases with Graham's law. Now, it's called Graham's law of diffusion. It applies both to the process of diffusion and effusion, which are not the same thing. Diffusion is when a gas, its container gets opened up and it has a chance to spread out to its like surroundings or environment. Like if I have a bottle of ammonia here, ammonia I know is a solution, but it's got vapors that can spread out. So if I open up the bottle of ammonia, then the ammonia molecules have to travel out into the room to eventually reach your nose. And when it starts hitting people's nose, they'll be like, oh, close that ammonia bottle. Because ammonia, of course, made its way to your nose. So that would be the diffusion of ammonia. Then the effusion of ammonia, or any gas, would be when you have a gas inside of a sealed container, like this. And now I want you to notice there's particles of gas. The dots, the individual dots are particles of gas. I know I've got the front lights off, but that is a tiny hole. It's an imperfection in the container, so the container is not perfectly sealed. There's a tiny opening in it. That opening, some of the gas particles, as they fly around, are going to find their way to that opening, and they'll hit where that opening is and just go flying out. That is the process of effusion. It is the loss of a gas from a container that has an imperfection, a tiny opening in it. The best example, of a real life example I can give you for effusion, is when you get a rubber balloon filled with helium. Rubber balloons filled with helium, they expand, and especially if they're blown up real nicely, man, they just shoot right up to the ceiling. And helium balloons are fun, and they're great. But 24 hours later, the helium balloon, even as big and as pretty as it was for the first day, it'll be on the ground the second day, because as that rubber stretches, it does form holes in it. It becomes porous. And so the helium, they're not huge pores, you can't see them with your eyes. But the helium, a tiny, tiny little atom, helium, will find its way out of those little pores in the balloon. So if you want a balloon to last, if you want a helium balloon to last, buy the Mylar balloon. They last for weeks because they don't really stretch. When you fill up a Mylar balloon, if you try to stretch out a Mylar balloon, they don't stretch very well. They're pretty rigid. So they'll inflate and become full, but there's really no place for the helium to escape out of when you have a Mylar balloon. So they'll go weeks. Much better. So anyway, that's diffusion and effusion. Graham's law will compare the rate of diffusion or effusion of two different gases. So imagine that we have two gases. Now, Graham's law only applies when the two gases are at the same temperature as well. So this really simplifies and narrows in when you can use Graham's law. So if you have two gases that are at the same temperature, the kinetic molecular theory says that same temperature means that they'll have the same kinetic energy. So that means the kinetic energy of gas 1 equals the kinetic energy of gas 2. Two different gases. Well, if the kinetic energies are equal, that means that the formulas for kinetic energy, which is kinetic energy equals 1/2 mv squared, 1/2 mv squared of gas 1 will equal 1/2 mv squared of gas 2. Now, when I give you a V term, that does mean the average velocity. We're talking about a lot of gas particles, some moving fast, some going slow, but this V would represent the average velocity of the particles. Now, when we're looking at Graham's law and thinking about what diffusion and effusion are, it is related to the velocity, but a comparison of the rate of diffusion and the rate of effusion, we're going to use that, and rather than calling it velocity, in this context of Graham's law, I'm going to use the word rate. So now, I guess the first thing I should say is this. I know the kinetic energy is 1/2 mv squared, but if 1/2 mv squared equals 1/2 mv squared, we can just multiply both sides by 2, and it'll cancel the 1/2 out. So let's go ahead and knock that out first. Get rid of the 1/2 on both sides. That and that can just get canceled out. If we multiply both sides by 2, then all the constant terms cancel out. So that leaves us with mass and velocity. The velocity I'm going to change to the word rate. Velocity, rate of 1 squared, rate of gas 2 squared, rate of diffusion or effusion. Now the mass I'm going to change to. If we're talking about the comparison between the mass of gas 1 and the mass of gas 2, like if gas 1 has heavier particles than gas 2, we would think, okay, the gas 1 is the heavier gas. Well, proportional to the masses of the particles would be the molar mass. It's not convenient to try to work with the mass of a particle. It's a ridiculously small mass. So proportionally to the masses of the gas particles is the molar mass of gas 1 and the molar mass of gas 2. So this is a change that Graham made when he came up with this relationship, was he addressed the mass of each gas by its molar mass and the velocity of each gas by its rate of diffusion or effusion. So this is a way that you could actually express Graham's law. It's not a complicated thing. Yeah,
Will rate be given if we have to calculate this?
Yes.
Okay.
At least the rate of one of them. You might be given one rate and you have to find the rate of the other one, but you'd have to know. You have to know 3 of these terms and you find the 4th. Okay. That's what Graham's law comes down to. It'll give you 3 of the terms and you find the 4th. So the way Graham expressed it, though, we're looking at a comparison of the rates of effusion. So Graham took this thing, he just did a little algebra manipulation with it. He took the rates and moved them all over to one side. And then the molar masses went to the other side. So on the left side, we already have rate 1 squared. So I'm going to keep that over on the left side, the rate of gas 1 squared. And then divide out the rate of gas 2 squared to the left side. And then on the right side, keep the molar masses over on the right side. So I know the molar mass of gas 1 is on the left at the beginning. Let's divide that out and send it over to the right side. So on the right side, the molar mass of gas 2 was already there, and then it's now being divided by the molar mass of gas 1. Now, since Graham wanted to create a relationship between the rates of diffusion, he's got the rate squared comparison here. So he actually took the square root of both sides, and this now cleaning this up, take the square root of both sides. The squared terms will just, the squared kind of drops off, and it looks like this. Rate of gas 1 over the rate of gas 2 equals the square root of the molar mass of gas 2 over the molar mass of gas 1. This is Graham's law. It's a comparison of the rates of diffusion of two different gases. So we have a couple of examples today that we're going to consider and work through using Graham's law. But before we do that, let's think about what Graham's law is telling us. What is the concept behind Graham's law? I was asked in the last class, is this on the equation sheet? And I had to go over there and look at it. No, it's not on the equation sheet, but I know that the AP exam asks about Graham's law. So if they don't have the equation for it, by the way, they do give you the formula for kinetic energy on the equation sheet. So if you know the formula for kinetic energy, you can derive Graham's law like we just did. So there's an option for you if you need Graham's law. Either memorize it or derive it. Either one is fine. What does Graham's law really tell us, though? I want you to notice, and a lot of people will get this, Graham's law is not difficult, but the one very common mistake that I see all the time, even from advanced students like you, is rate of gas 1 is on top, on the left side, and people will tend to put molar mass of gas 1 on the top. If they had gas 1 on the top over there, they want to put gas 1 on the top over there. That is a mistake. Yes?
Why wouldn't the first equation, molar mass 1, rate 1 squared, be like easier to work with?
I like that first one myself. I prefer this. And normally for myself, when I'm solving a Graham's law problem, I use this. So this is fine. There's no difference between that expression and that expression. They're the same thing. But yeah, that whole square root thing, and a lot of times you have to solve for an unknown molar mass. I don't know. I just like that better. I think that's easier to use. But you'll always see Graham's law expressed like this. So I give it to you like this. What is this telling us is the relationship? If gas 1 is faster diffusing, I'll say this again. If gas 1 is faster diffusing, that means that this left ratio is greater than 1. Would you agree with that? If gas 1 diffuses faster than gas 2, then this fraction is greater than 1. Well, if this fraction is greater than 1, then this must be greater than 1 as well. Yes? Because the two fractions are equal to each other. So if the fraction on the left is greater than 1, then the fraction on the right has to be greater than 1. Okay? So what does it tell us about the molar masses of the two gases? The one that diffuses or effuses faster is the lighter gas, because the other gas must be heavier. If the numerator is bigger than the denominator on the left, that means the numerator must be bigger than the denominator on the right. So that means that the gas 2 must be heavier. So, and this is worth writing down for yourself, the faster diffusing gas is always lighter. The faster diffusing gas is always the lighter. There's an inverse relationship. Lighter gas, the faster it goes. Now, that is very consistent. I'll pause for a second for you to write that down. The faster diffusing gas is the lighter one. Yesterday we looked at a calculation of the root mean square velocity. Now it should make sense, and we talked about this qualitatively yesterday too. The lightest gas, because if we look at just a couple slides back, here, this velocity of particles is the square root of 3RT over the molar mass. And we decided that if the molar mass is high, then the velocity is low. So light particles will move the fastest. And I said, what element on the periodic table would be the fastest moving particles? Everybody agreed hydrogen, because it's got the smallest denominator. That is consistent with what Graham's law says. The faster particles moving, the faster it's going to diffuse. The faster moving particles are going to escape out of the container the fastest. So this is very consistent between those two concepts: speed of particles, rate of diffusion. Okay, now the first example problem I have, we're going to call this the Mickey Mouse example. It's very simple and straightforward. It's pretty much just putting some numbers in and see if you can get the correct answer doing the algebra. The rate of infusion of a particular gas, so we have an unknown gas here, was measured and found to be 24 milliliters per minute. How much volume per time? That's a rate of diffusion. It's losing volume. Under the same conditions, the rate of diffusion of methane, one whose molar mass we know, is this. So what is the molar mass of that unknown gas? You don't have to identify, just figure out what its molar mass is. Take a moment and see if you can do that one.
Enough. Wow, Mr. Mo, I'm actually 3 for 3. I got 63. I got 63. Did you get that?
Like I said at the beginning, when you get an answer, inspect it and make sure that it makes sense.
It does make sense.
Should the unknown gas be heavier than methane or lighter than methane? Well, let's see. The unknown gas diffuses slower. Does that make it heavier or lighter? Heavy. Yeah. If it diffuses slower, if it's got a small rate of diffusion, it must have a high molar mass. There's an inverse relationship.
Wait, Mr. Mo. So when it diffuses slower, it's high molar mass, and when it
Yeah,
diffuses faster,
that's right.
slow.
The way that I think about this expression, this algebraic expression, each gas is allowed to be in the numerator once in this expression. So methane is allowed to be in the numerator once. Therefore, on the other side, the unknown has to be in the numerator once. That's how I remember Graham's law. Each one gets a turn being in the numerator. So yeah, just put your numbers in. It's just you have 3 of the terms. You need the 4th, so do the algebra. The rate of M was 47.8. I have both rates, so I'm not even going to put the units in there. 24 is the rate of the unknown. Molar mass. Now, you'll see methane gets used a lot when we're doing Graham's law, only because methane has a molar mass of 16, a perfect square. So, yeah, you'll see that methane shows up a lot in Graham's law problems. Yeah, so it looks like this, and then just solve it and make sure you don't mess up your algebra. So you should get a molar mass of 63. I got 63.5. I heard you say 63.7. So
I got 63.5.
yeah, it's fine.
Yeah, for I got 16 as my molar mass. Yeah, it's a 0 right there.
Something close to that.
Wow, Mr. Moore, really?
Too easy?
No, we both got 63.5, but he still wrote 63.7.
Oh, I thought you said 7.
Yeah, but he's wrong. I'm right.
Guys, it depends on the molar mass you use.
What'd you use?
I used
16.05.
16.05.
I did 16.0.
Yeah, okay. All right, so, and I would have used 16.02, so
Oh.
Rishi, I'm on your side.
You must have. I like that.
All right, so if this one was a Mickey Mouse example, the next one we're going to call an Iron Man example.
Oh. Wait, does that mean like? Oh wow. It's because I did the infinity snap.
We're going to a PG-13 example now. So yeah, we have to put on our big boy and girl pants and see if we can make it through this. So I'm going to give you a couple minutes. I didn't really mean that.
Oh. Fuck. Well, I'm locked in now. Don't even worry.
See if you can work this one out.
See if I can. It takes methane.
How many seconds are in a minute?
Like this guy is actually like destroyed. 50 seconds whole. No, no way I'm far away. If there's a molar ratio. I don't even know what I'm saying. 50. Wow. Already done. Disgusting rat. I didn't start yet.
Wait, what is the longest?
H4. So 16. You don't need to. You don't. Rat. Okay, we don't need to hear the entire class. Watch.
2.4 times slower.
Hey. Are they? What is happening? Wait, it takes methane?
No, the molar mass is less.
Molar mass is more.
Oh, more, yeah.
Oh, I see my balankadonk. Oh, Abhinav, I see something.
Why didn't you watch the video I showed you? I
Yo,
sent it to you for a reason.
I have so much ore, just don't even talk to me.
38.5.
Wait, I
I
think
haven't even used the formula though.
I think I'm. That doesn't help.
He's too cool for that.
He's Mr. Orange. Wait, you watch me cook? I think I'm gonna get it right. Wow. I'm far. 50? Dune, Dang, Wing Wang, Dune Ching Ching Ching. Wow, I got the worst answers over. I got 2, bro. What?
Wait, did you get this?
Yeah.
Did you get this?
Yeah.
That doesn't make
Yo.
sense. You get
Yo, Mr. Moore, is it a 1-digit answer or a 2-digit answer?
what you get.
Ah, he's right. I mean, we already knew that, didn't we? Yo, Aki, what you do? Let me get my. Oh, wait. I got my big brain on. Hold on.
What did you get? Oh, okay, what are you guys using as the rate? The rate isn't 120.
Exactly. Yes. You subtract both of
It's
them.
like it's 1 over
It's
100.
Yeah, that's what I was gonna say. It says that methane takes 50 seconds to go through the tube. Is that the rate of methane?
Oh, you do 50 divided
No,
by
that's the
100.
time.
Oh, you do 50 divided by 100.
So yeah, I want you to consider this. I'm gonna go ahead and try to do some kind of a
You do 50 divided by 120.
picture of this,
Wait, what if you do 50 divided by 100? Shh.
even with the help of making straight lines. My picture's still kind of lame.
Oh.
So we have a 1 meter tube with our methane
All this amazing workout.
going through in 50 seconds. The unknown goes through in 120 seconds. Which one got to the end faster? So does that make methane faster diffusing? Yeah. But methane took less time. So it turns out that time is inversely related to rate. Time is inversely related to rate. If you're given time, now in this case, you could have actually calculated the rate of both of them. You could say, okay, the methane is 1 meter over 50 seconds. And actually find the rate. 1 divided by 50 is 0.02. And then the unknown was 1 meter over 120 seconds. And find the rate. And you can just plug in the rates. However, you could do it faster knowing this, that the rate of methane over the rate of the unknown equals the ratio of the time of the unknown over the time of the methane. Because the time is inversely related to the rate, this is true. Now, Graham's law says that the rate of the methane over the unknown equals the square root of the molar mass of the unknown over the molar mass of the methane. So, the far left ratio is equal to the far right ratio. That's what Graham's law says. But since we understand that time is inversely related to the rate, you could just flip the methane and the unknown in that. Now, this is why. If I just use a different color, I'll show you. remember that the rate of methane is up there in the left corner, 1 meter over 50 seconds. Divided by the rate of the unknown was 1 meter over 120 seconds. So look at how this fraction works out. This thing simplifies to 120 over 50, which is the time of the unknown over the time of the methane. Okay? So just putting the numbers in here, this was 120, this is 50, and this is 16. Again, molar mass is 16, nice round 4 answer. So solve for the molar mass of the unknown, it's 92 around there. All right, nice.
B, what has happened to you? Don't worry, bro. I'll perform my honor.
I know for sure there is a question like this in the practice test. I get lots of questions about that. So, yeah, you'll see that soon. This weekend, do all those homework exercises, because you'll do a lot of them between now and tomorrow. So you'll knock a lot of them out of the way before you get into the weekend, and then you can do the rest of them over the weekend and some of the practice tests this weekend. Finish well.
Got you.
Wouldn't it be nice to finish well in this
Yeah.
class with nice high grades?
We done with chapter 5.
You know, I thought I would like.
As of this, yes. All we have is examples now.
I thought I would like chapter 5.
So we have to know all the derivatives. Like,
No, he said we don't have to.
Either memorize them or derive them.
Oh, never mind.
And you're welcome to any time look over at that equation sheet and see what you're given on it. Don't look at it for the first time when you're taking your quiz. There's a stack of them over there. You're welcome to take those at any time. If you want to just take one with you, go ahead. So that you know what's on. Okay, now I know that we have quite a bit of time left this hour, but in my first hour class, we had just started this one, and I said, oh, let's do this, and we had like 15 minutes left in the hour. I said, okay, take a few minutes to try this. And then the fire drill happened. So I said, well, okay, we got back in for the fire drill. There's less than 5 minutes left. I said, we'll just wait until tomorrow. So with you, we'll just wait until tomorrow with you as well.
Thank you.
Okay? So
Free out.
you can.